So this class, we will be doing some very interesting physics related to your syllabus. Obviously, it is going to be a bit mathematical, right? Because you are in 11th standard. Mathematics should be a part of physics now, correct?
Yeah.
Yes.
Yeah.
That's right.
Okay, so let's start. So the topic that we will be discussing is called as rotational motion, right?
Okay.
Just a minute. Okay, so I hope you can see the white screen, students.
Mm.
Rotational motion, correct?
Yes.
Now, before starting rotational motion, can anyone amongst you tell me what is the difference between? There are two types of motion. Motion is broadly divided into two types. The first is translational motion, correct? Translational motion. And the second one is rotational motion. So can you tell me what is the difference between them? Yes, anyone?
I guess by the name, I'll just guess about that. Rotational motion means it's talking about the motion that moves through as kind of circle kind.
Okay, okay. What about translation? What about translation?
Translational, I guess it's about some kind of really straight line with a kind of different kind of directions.
Okay, fine. So I have a small small demonstration for you. Okay, a very simple demonstration, a very real life based demonstration. Okay, I hope you can see my screen now.
Yeah.
Okay.
Yeah.
Now let us say this phone is my object. Okay, can you see the phone?
Yeah, I can see the black
phone is the object. So just try to observe the motion of the phone. Everyone, this is very important, very basic. See, can you see the motion of the phone?
Yeah.
What kind of motion is this? Tell me. Rotation
Kind
or
of
translation?
circular. Yeah.
Rotation or translation?
That's a translation.
Why?
Yeah.
Why that's a translation? Tell me.
Because it's not rotating.
It's not rotating. Okay, good.
Yeah.
Let me try this motion. Tell me what kind of motion is this? What kind of motion is this?
Rotational.
Are you sure?
I think.
See, just see the motion. See the motion, guys. What if I tell you this is a translation?
Yeah, that's rotational motion.
Sadly, that's a translational motion. Yes.
Oh.
Okay.
I'll tell you why. Now tell me what kind of motion is this? For example, what kind of motion is this?
Translational.
This is rotational. Come on.
That's rotational.
Exactly.
Yeah.
So
no, that's rotation.
Correct. So now you must be a bit confused, right? I'm not able to understand how to find rotational, how to find translational, correct? Okay, great. I will explain this. I will give you a definition of it, and then I think you will be able to understand it. All right? Okay. So let's go for the definition. So the first thing is, let us say what is translational motion. Translational motion. Now, you know, every body in this world, it is made of particles, right? Every body is made of particles, correct? So let's take an example. I was talking about my phone. So can I say my phone is actually made of many particles? Yes. Let's say this is my phone. My phone is made of many particles. Let's say particle 1, particle 2, particle 3, many particles. I'm just naming few of them, right? I'm just naming few of them. I'm not naming all the particles, okay? Otherwise, the lecture will end and I will still be naming the particles, okay? That's how it is. Okay, so what is the meaning of translational motion? In translational motion, try to understand the definition. In translational motion, every particle will have same velocity at every instant. Are you guys able to understand the meaning of this? Every particle will have same velocity at every instant, at every moment, or you can say at every moment. Now, what does that mean? What does that mean? Let us try to understand. Let's take an example. My body is moving in a straight line, okay? My body is moving with this velocity. The velocity is v. It is moving in a straight line. Can I say, if my body is moving in a straight line, this particle is also moving with same velocity, this particle is also moving with same velocity, this particle is also moving same velocity, right? Correct?
Yeah.
So whenever you notice that each and every particle is moving with same velocity, okay? Each and every particle is moving with same velocity at every instant. That kind of motion is called as translation. Correct?
Translation.
In a very layman language, translation motion is when orientation of the object is not changing. Okay. You must have noticed in the first two examples, my orientation of the phone was not changing while moving, right? Are you understanding this?
Yeah.
So whenever you notice that the orientation of the object is not changing while moving, that kind of motion is called as translation motion. Is this very clear?
Yeah.
Now I will show you the same example. I am sure you will be able to understand all this motion are translation. Okay, try to observe it again. I hope you understood the definition now.
Yeah.
Okay, see the phone. Don't you think even the phone is going like this? At every moment, each and every particle of my phone are having same velocity. See, it's not circular, isn't it?
Yeah.
Are you understanding this, everyone? It's not rotating, correct? It's not rotating. I hope this is clear. See, this is translational. It looks very fancy because my phone is not rotating. If my phone turns while moving, if my phone is turning, then this is, do you think this is translational? No, this is not translational. Understood? This is translation. See, my phone is, nothing is happening to my phone. It was lateral, again it is lateral. See, nothing is happening. It is translation. Understanding? See, every part of it is translation. Similarly, let's take this pen. Let's take this pen. Is it translational? Yes. See, its orientation is not changing, correct?
Yeah.
But now is it translational? Now is it translational? No. Its orientation is changing, isn't it?
Yeah.
Perfect. Now, let us go ahead. I hope you understood what is translational, right? Okay. So let's go ahead and understand what is rotational motion. Okay. Rotational motion. What is rotational motion? Now, when I talk about rotational motion, you need to understand something. Rotational motion basically means object is rotating about a fixed point or a fixed axis, correct? Are you understanding this?
Yeah.
It means the object is rotating. Now, like the best example, the fan which is just above you, it is rotating, correct?
Yeah.
And what is the axis of your fan? The rod, right? The rod.
Oh, yeah. Yeah.
So there are plenty of rotational motions that we observe. The idea is it is rotating about some fixed point or any fixed axis, correct? When I do this kind of motion, let's take an example. See, this is rotation. This is rotation, correct?
Yeah.
And this is pure rotation. This kind of rotation is called as pure rotation because there is no movement, right? There is just rotation, correct? Even see, let's take my arm. Can I say my arm is rotating? Yes, see, my arm is rotating. Correct?
Yeah.
Yeah,
My arm is
especially on
Have
the
rotating.
its
joints.
fixed points.
Correct. Very good.
You
About a
joint
fixed
the
point.
fixed.
Great. But now there is a very interesting thing that we need to understand. A very important thing that we need to understand. See, we know a body is made of many objects, right? Correct? A body is made of many particles.
Yes.
When a body rotates, let's take an example. I'm writing something over here. Okay, a small object rotating, a small diagram. So let's take an example. This rod is rotating about this fixed point. Okay, this is the fixed point, correct?
Okay.
When I draw cross, it means this point is fixed. Okay, and the rod is rotating like this. It is having some angular velocity. I hope you're aware of angular velocity, omega, correct?
Yeah.
Omega basically tells you how much angle you're covering in a given time. Okay. Now, when a body rotates, see, can I say this body is made of many particles? Let's say this particle is particle 1, this particle is particle 2, this particle is particle 3, correct?
Okay.
Now you tell me, whenever a body rotates, first, every particle on that body, whenever a body rotates, every particle on that body moves in a circular path. A very important observation. Moves in a circular path. Check. Try to understand this. Try to visualize this. See, your rod is rotating, right? After some time, your rod will reach here. Let's say your rod will reach here, right? Correct?
Yeah.
After some time, your rod will reach here, isn't it?
That's right.
Where has your particle A reached? It has traveled in a circular path here, right?
Yeah. Yeah.
Particle B has traveled like this, right? See?
Yeah.
Particle C3 has traveled like this. See? That is the beauty of rotation. See, there is a very big difference between rotating and circular motion. Many students get confused between rotational motion and circular motion. Getting it? So, if a body is performing rotational motion, can I say every particle on that body is moving in a circular path? Have you understood this?
Yeah.
The best example, you must be having the fan just above you, right? Try to concentrate on any point on that fan and you will notice it is performing a circular motion. Check it, quickly check it. Isn't it? But do you think their center is same? Do you think the center of all the circular path is same? No. Yes, the center is same. See, every circular path is having its center on the axis.
Yeah.
Second, center of all the circular path is same, but they have different radius, isn't it?
Oh, yeah. Yeah.
They have different radius. I hope this clearly makes sense to all of you. So whenever an object does rotation, you will always observe this idea. You will always see this kind of conclusions. Okay? Quickly note it. I hope now you understand the difference between rotation and translation, right?
Yes.
Yes. Okay, once you're written, let me know.
Okay, let's continue.
Okay, let's go ahead. Now, Let us take a very simple example of rotation. Okay.
Okay.
A rod is rotating. Okay, just a minute. I'll take a very simple example. This will be very easy for you. A rod of length 1 meter rotates about its axis, sorry, about its end. Okay, about its one end. Okay, a rod of length 1 meter rotates about its one end. Okay, with and angular velocity, with an angular velocity of 1 radian per second. What is the meaning of this? What is the meaning of having an angular velocity 1 radian per second? Yes.
That means that
What is the meaning of having angular velocity as 1 radian per second? I am sure you are aware what is the meaning of angular velocity. Angular velocity basically means omega is equal to 1 radian per second, correct?
okay.
Yeah.
It means it is rotating in such a way that in every 1 second it is covering 1 radian angle.
Mhm.
In every 1 second it is covering how much angle?
One red rod.
I hope you understand the meaning of 1 radian, right?
Yes.
Perfect, perfect. So let's go ahead now. Let us try to understand this. So see, what was my rod doing? How is my rod? See, my rod is something like this. See, like this. It is fixed at one end, okay, correct?
Mhm.
And this is the rod, correct? Do you agree with me? Correct?
Yep.
So if my rod is rotating, can I say my rod is actually moving in a circular path, something like this? See, correct?
Mhm.
Do you agree with me or not?
It's kind of rotating.
Exactly. It's kind of rotating. That's correct. So can I say at time t is equal to 0, my rod is over here, right? So after some time, at let's say time t is equal to 1 second, at time t is equal to 1 second, my rod will be here. Correct?
Okay.
And how much angle it must have covered? Tell me. How much angle it must have covered?
I guess omega.
1 radian, exactly. Because
Okay.
it is covering 1 radian in every 1 second, isn't it?
Yes.
But tell me, just tell me, let us talk about this particle. Let us talk about this particle, the particle exactly at the middle, okay? The particle exactly at the middle, okay? And let us take this particle and let us take this particle, okay? Particle 1, particle 2, and particle 3, okay? Correct?
Okay.
Now tell me one thing. When the rod traveled from time t is equal to 0 to time t is equal to 1, can I say this particle 2 has traveled this path?
Actually, yes.
Agreed?
I agree that.
And particle 3 must have traveled this path. See?
Mm-hmm.
Do you agree with this or not?
Yeah, actually, I'm seeing it. Yeah, I do that. I do believe that.
Now tell me one thing. They reached at the same time, isn't it? They reached at the same time, correct? In 1 second.
Yes.
But don't you think particle 3 has traveled a greater distance compared to particle 2?
Yeah.
Well, yeah, I do that because particle 2 is closer to the center or the fixed point.
Exactly. And the best part, particle 1 has traveled 0 distance, isn't it?
Because it's the center.
Exactly. So can I say velocity of particle 1 would be 0? I'm very sure about it.
0 meters per second.
Do you agree with me?
Yes, we do.
Now tell me, don't you think velocity of particle 3 will be greater than velocity of particle 2?
Yeah, it does.
Exactly. And there comes a very beautiful formula that velocity of any particle, whenever an object is performing a circular path, velocity of any particle is R into omega. Understanding it? What is R?
Yeah.
What is R? It is a distance from the center. Distance from the pivot point, right? Pivot, correct?
Mhm.
Pivot or the fixed point. I hope this part is very easy for both of you to understand. And that's how the concept is. That's how the concept of rotational motion is. Okay. I am sure now you are able to understand these formulas in a better way, right?
Yes.
Perfect. Perfect.
Yes.
Okay, quickly note it.
Okay, we're just taking this notes.
Sure.
It's
Sure.
important.
Sure. I hope this is a part of your syllabus, right? Completely.
Yeah.
Good.
Yeah, okay.
Okay. Done?
Yeah, done. Hayli Charasa?
Yes.
Charasa?
Yeah.
Back, okay, Mr. We done.
Okay. So now comes, now I'll summarize it. I will summarize it now. See, now what is the difference between translational motion and rotational motion? See, in this motion, orientation remains same, right?
Yes.
Yeah.
Remains same at every instant, right? At every instant, the orientation remains same, correct? Here, the orientation, what happens? Changes.
Yeah.
Second point. Let's talk about the second point. The second point is each particle will have same velocity at every instant, right?
Yes.
What about in the rotational motion? They will have different velocity, isn't it? They will
That's
have
right. Every particle will have
different linear
different kind of
velocity.
velocities.
Linear velocity. As we all know, velocity is given by v is equal to r omega. So greater the r, greater will the v, correct? Omega is constant for the body. Omega is constant for the body. Okay. Omega is constant for the every particle. Okay. Omega is constant for every particle. Omega is constant for every particle. Clear? Any doubts? Tell me. Any difficulty?
No.
Okay. So
All
now,
clear.
perfect. So I have a small example for you. Okay. So I want you all to understand this. See. So now we'll be talking purely about rotation, correct? Now we will be talking purely about rotation. So I hope you understand what is the meaning of rotation and what is the meaning of translation, correct? Correct? Okay. Now, tell me, For example, let's talk about the door at your home. Okay. Let's talk about the example of a door. Example of a door. Okay. The door at your home. Fine.
Yeah.
So let us take this is your door. Let us take this is your door. And the door is hinged, right? It has a hinge support, correct? So the door is having some kind of hinge support over here, right? Here, 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 here. Do you agree with me? These are hinge support. All right? Hinge support. Now my question to you is, you want to open the door. What is the meaning of open the door? To open the door, we will have to rotate the door, right? Correct?
Yes.
This is the only possible thing, isn't it? If you want to open or close the door, what is the method for that? The only method is you will have to rotate it, correct?
Yeah.
So let us understand. Now what we are going to do is, we are going to understand whether I can rotate something with the help of a force or not. Okay. So now I have a very simple exercise for you. Try to apply a force in this direction. Okay. Try to apply a force in this direction. Do you think your door will rotate? Or you can open the door? Tell me. Do you think you can open the door?
Yes.
Are you sure? Think about it.
Well, it depends on the direction where you apply the force.
Yeah, the direction is like this. The direction is exactly like this.
No, it doesn't open the door because it's just pushing straightly to the center.
Exactly. So this force cannot open the door, right? Impossible. Correct?
Yeah.
This force cannot open the door. But now, do you think if you apply a force like this, if you apply a force exactly at the hinge, if you apply a force like this, do you think this force will open the door?
See, I guess no.
No. Very good. Very good. Very good. What is it? Are you able to understand this direction? Are you able to understand this direction? This means into the plane, correct?
Yeah.
And what is the meaning of this direction? Out of the plane, correct?
Okay.
Correct. So I know these two forces cannot open the door. This force cannot open the door, and even this force cannot open the door, right?
Yeah, that's right.
But tell me one thing. If you apply a force exactly like this, exactly like this at this point, and let's take an example. David, you apply a force of 10 Newton, okay, at this point, okay? This is force by you. And let's say Haley apply a force of same magnitude, that is 10 Newton at this point. Tell me, for whom it is easier to open the door? I am very sure you will agree with me that now you both can open the door, right? Correct?
We both open the door, but the first one's gonna be easily open. That can easily open the door is the 10 Newton with the black circle.
Very good. So you're trying to say this will help us with this force. If you apply a force like this, it is easy to open the door, right? It is easy to open the door, correct?
Yes.
Why?
Because it's far away from the center.
It's far away from the center. Or you can say this force is at a greater distance from the center, and this force is as a lesser distance, right?
Yeah.
So can I make a statement? Only force is not enough for rotation, correct? Only force is not enough for rotation, correct?
Okay.
Do you agree with this statement?
Yeah, actually, that's right.
The best example would be this one. See, even this guy is applying a force and even this guy is applying a force, but door is not rotating. See,
Mhm.
do you agree with me?
Yes.
Yes. So that is the basic understanding, that only force is not enough for rotation. I hope this clearly makes sense to you. Understood this? Quickly write it. Quickly write it.
Yeah, actually, I did write that.
Okay. So next, let me take one more example. The other example would be, let's take this is your floor. Okay. Let's take this is your floor, horizontal floor, right?
And Mitchell, can I just pause you here?
Sorry.
Can we just take the example of the car, the wheel of the car?
Yeah. I'll take the example. I'll take that example. Don't worry. I'll take this example. I'll take that example. Don't worry. Okay. So let's take an example. You have a rod here. Okay. You have a rod here. Okay. This is a rod. Fine.
Yeah.
This is a rod. Now, my question is, let us say you apply a force F in this direction, and then you apply a force F in this direction. Okay, correct?
Okay.
Do you think your rod will rotate? Try. You can try it. You can try that. You can try that. Apply a force in this direction and apply a force in this direction. Do you think a rod will rotate?
No, it
Are we applying the same direction?
Very good.
well,
I think you're
no,
trying to,
you
it
would
will
just
not
translate.
rotate. Very good word. Very good, Hali. No rotation, only translation, correct?
Yeah.
I hope you all will agree with me.
Yes.
The basic idea is like this, how it will move, I'll tell you. After some time, my rod will be here. After some time, my rod will be here. Correct?
Okay.
Agreed?
Yes.
Yeah. So this is how it is. So I hope you agree with me. There is no rotation, but only translation. Now, this is one more example. By which I can prove you only force is not enough for rotation. Correct? Exciting.
Mhm.
Now let me take one more example. Now this will, I think this will might confuse you or maybe excite you. I'm not sure. Let's see. Again, the same rod on the horizontal surface. Okay. It's a horizontal floor. Correct. Now what is happening is you are applying one force like this and you are applying one force like this, same magnitude. Tell me what will happen. Do you think there will be
actually,
translation?
this one will rotate.
This will rotate. Okay.
Yeah.
Okay. It will rotate. Very good. What about translation?
There won't be any kind of translation because there will be center at that time because both force have the same kind of force. Both people acting on the same kind of force.
Good. But how will you define it? See, for translational, the basic definition is for translation, we need net force, correct? Agreed? Correct?
Okay.
And in this case, there is one force in the downward direction, one force in the upward direction. Can I say net force is 0? Yes. Correct? Do you agree with this? Hello?
Okay, yeah, I do that, but I'm still confused about the net force.
Okay, no problem. See, what happens is, I hope you agree that force is a vector, correct? Force is a vector, right? So
yeah, that's right.
if this force is in upward direction, one force is positive other force is negative. So plus minus 0. Agreed? Net force
Yeah.
means total force. Net force means total force, right?
Yeah.
Similarly,
So
here, see, here there is a positive force, there is a positive force, so net force is 2F, correct?
that's right. Yeah.
And that is why there was translation. Can you see this? There was
Mhm.
translation in this. Agreed? Agreed up till here?
Yeah.
So now what is our conclusion? See, I'm trying to come to the conclusion part. You know, my goal is to bring you back to the conclusion. So
Okay.
first conclusion. When an object is at rest, okay, when an object is at rest, first, for translation motion, okay, for translation motion, what do we need? We need net force, correct?
Okay.
Second thing, for rotational motion, what do we need? What do we know? Only net force is not enough, right? Only force is not enough, correct?
Yes.
Do you agree with me?
Yes.
And that is when what really matters is where you are applying the force.
Yeah.
Where are we applying the force also matters, right?
Yes, that's right.
And that is when your new term that you are very much confused in life, I'm sure, which is called as torque. Okay.
Mhm.
There is a new mathematical term defined for you, and that is called as torque. Okay. That is called as torque. I hope you understand this.
Yes.
So for rotational motion, what do we need? For rotational motion, what do we need? We need torque, correct?
Okay.
If there is no torque, there won't be any rotational motion, correct?
Okay.
And if there is no net force, there won't be.
There won't be any translational motion.
Very amazing, very good. Quickly write this. Now I will define torque for you.
Okay. First, let's just finish this note. Just additional questions.
Okay.
You'll have drink.
Any doubts?
No.
No. Everything is clear.
Okay. Quickly note it.
Okay. Highly Charusk.
Yes. Any doubts?
Alcharaska?
I finished.
Okay.
He's finished. Everyone's finished.
Let's continue.
Okay. Okay. So let's go ahead. Okay. Now I will introduce torque for you. I hope you are understanding the sequence, right? I hope you guys are understanding the sequence. Yes. Perfect. So torque is equal to magnitude of force multiply by magnitude of force multiply by, now this is very important, perpendicular distance. Okay, perpendicular distance between line of action of force, okay, and pivot point. Agreed? What is the meaning of torque? Torque is nothing but the product of magnitude of force and perpendicular distance between line of action of force and the pivot point. Check it.
Okay.
Okay, what is the meaning of it? I'm sure you must be worried. What is line of action of force, right? Correct, line of action of force, correct? That's a very simple thing. That's a very simple thing. So let us say the force is like this, correct? Let's say the force is like this. So this line in which this is called as line of action of force, correct?
Okay.
Simple.
Yeah.
For example, there is a force like this. There is a force like this. So what is the line of action of force? Like this, correct? Any doubt?
No.
Okay. So this is all about this particular thing. Okay.
Okay.
Fine. So now let us take some examples. Let us take some examples. See, I'll go like this. So, for example, let's say you have a rod here. Okay, you have a rod here. I will take two cases, two examples. Okay, I'll take two examples. Let us say you have a rod here. This is your rod. Okay, it is pivoted here. It is pivoted here, which means it is fixed here. Correct?
Yeah.
Now what happens is, I want to rotate this rod. I want to rotate this rod. Okay. So what I'm doing is, one first person is applying a force like this on the rod. Correct? Let's say the force is 10 Newton. Okay. And the second force is applying like this. The second person is applying like this. See, the second person maybe this on the rod. The second person is applying a force like this. Okay. And the third person is applying the force like this. Let's say there is a third person. The third person is applying, let's say the rod is here. The same rod, okay, exactly same rod. The third person is applying the force here, correct? Now we know to rotate something, we need torque, right? And we also know, greater the torque, easier to rotate. Easy?
Yeah.
To rotate.
Greater the torque, easier to rotate. Very simple mathematics. So tell me, in the first case, let's say length of my rod is 1 meter. Okay, length of my rod is 1 meter, and this distance is exactly half meter. Okay, this is 1 meter. Okay. So how to find torque in first example? Very simple. I will first draw my line of action of force. See, this is my line, right? Correct? See? Correct? Yes. And this is my pivot point. Correct? So tell me, can I say this is my perpendicular distance? Exactly half meter. Correct? So torque in this example is magnitude of force, which is 10 multiplied by perpendicular distance, that is half. So can I say this is nothing but 5 Newton meter is a torque, correct?
Yeah.
Why 5 Newton meter? How did I found the unit Newton meter? Because force is Newton and distance is meter. Is it?
Yeah.
Here. Tell me, what is a torque in the second example? What is a torque in the second example?
Zero.
Zero.
0. Why?
Because
Zero.
caricature.
Exactly. The distance is 0, right? Perpendicular distance is 0. Force is not 0, but the perpendicular distance is 0. What is a torque in the third case?
10.
10 Newton meter. So my friend, can you tell me in which case it is easier for us to rotate? In the third case.
The third year.
Yes.
And the best part, whatever examples you have in your real life, let's take an example. Let's take an example, your door. Okay, the door at your home. I am sure, let's say this is the hinge part. Let us say this is the hinge part, okay, the pivot line. I am very sure you must have noticed there is a handle exactly at the end, right, on your door. Why do we have the handle at the end and not the handle at closer to the pivot? What is the reason?
Because we rotate an object.
Correct.
To rotate an object, we should have the
exactly.
We should
To
arrange the
make
position.
rotation easy, right?
Yeah.
Even the similar example is there in your car door. Have you seen your car door? When you open the door of your car, when you open the door of your car, you must have noticed a very interesting thing that on your car door, that part is exactly at the end, right? No?
Yeah.
When you have a car door, the handle is at the end, right?
Exactly. Yes, that's right.
So every real life example works on this. Every real life example works on this principle. So to rotate something, what do we need, students? We need torque. And what is torque? I have already defined you, right? Force into perpendicular distance of the line of action of force and pivot point, correct?
Yeah.
Yes, that is the beauty of it. Any doubts?
No.
Are you sure?
Yeah, everything is clear.
Okay. Let me give one more example. Okay.
Okay.
So let us say the example which we took initially. Let us say there is a bar here, correct? This is a horizontal floor. This is a horizontal floor. And what do we know is, we know that when you apply a force like this, and then you apply a force like this, you already said there is no rotation, correct?
Yeah.
So what do you mean by there is no rotation? You are damn sure there is no torque, correct? No.
Because the forces are not perpendicular.
No, not that way. There is no net torque. Individually, they are creating a torque. I'll tell you how. Let us take, I'm considering the center, correct? I'm considering the center. All right. So let us say this is at a distance D. So can I say even this will be at a distance D, right? Fine.
Yeah.
Now, understand this idea that torque is a vector quantity. Torque is a vector quantity, correct? So it has a direction. It also has a direction, isn't it?
Yep.
So the idea is, let us call this force as F1. Let us call this force as F1 and let us call this force as F2. So concentrate on F1. Torque because of F1. Okay. Torque because of F1. So don't you think F1 torque because of F1 is equal to what? Tell me. At the center, it is force into D, right? correct?
Mhm.
Similarly, can I even say that torque because of F2 is equal to F into D, correct? Yes or no?
Yes, yes.
But they are opposite torque. Why they are opposite? Try to understand. This force is actually trying to move the system like this, right? It is trying to move the system like this, isn't it?
Yes.
And this force is trying to move the system like this, isn't it?
Mhm.
And don't you see they both are having same torque? They both are having same torque. This one and this one, right?
Yeah.
So same torque, but opposite direction. Don't you think they will cancel each other?
They will.
So what will be the net torque? The net torque will be 0, correct?
Yeah.
And that's why your body doesn't rotate. I hope you agree with me.
We did.
Same torque, but in opposite direction. Clear?
Yes.
The torque is same, but the direction is opposite. Now let's concentrate on the direction. Let's focus on this. Hence, no rotation. Hence, net torque is 0. Hence, net torque equal to 0 and no rotation. Now let's conclude this. See, don't you think this is this one, F1? Concentrate on F1. I hope you guys are hearing me. Concentrate on F1. Don't you think this is trying to move the system clockwise?
Yes.
So can I call this? So I will call this torque as what? Clockwise, right? Clockwise torque, correct?
Yeah.
I hope you understand how I called it clockwise, right?
Yeah.
If this is moving it clockwise, what about this? This is anti-clockwise, right?
Yes.
So if this is anti-clockwise, I will call this one as what? Anti-clockwise, right?
Mm.
I will call this torque as anti-clockwise. So why is my system not rotating? Why is my system not rotating?
Same torque, but in opposite direction.
Sorry?
Same torque, but in opposite direction.
Very good. Amazing, amazing, amazing. Very good, very good. So net torque is 0. Net torque is equal to 0 when clockwise torque equals what? Anti-clockwise torque. Correct?
Yeah.
Mhm.
And this condition is called as equilibrium condition. Okay, I'll write that, don't worry.
Okay.
There is some, I hope you must have heard the word equilibrium, right? Equilibrium.
Yeah.
So what is the meaning of equilibrium? Equilibrium basically means,
Constant means equal.
yeah, the net force should be equal to 0 and the net torque should be equal to 0, right?
Mhm.
Yeah.
The net force should be equal to 0 and the net torque should also be equal to 0. Do you agree with me?
Yes.
Okay, so quickly write this part fast. So any doubts, let me know up till here.
No.
Okay,
Everything is clear.
perfect. So now let's talk about one more example now. Okay.
Okay.
Okay. I have a very practical example for you now. I have a very practical example for you now. Let me show you that example. This would be very interesting, you know, this would be surely very interesting for all of you. This will make you think actually. This will make you think. That's the goal of my class, okay? Not just you teach the concepts.
Okay.
Okay. So Can you see my calculator?
Yes.
Yeah.
Assume the calculator to be like a, a uniform calculator, which means mass is uniformly distributed. All right.
Yeah.
Correct.
Okay.
Now my question, I have a small question for all of you. You notice when I hold this calculator at the center, I can hold it, right? See, it's balanced, right?
Yeah.
Easy.
Yes.
It's very easily balanced, isn't it? See,
Mhm.
but as soon as I keep my pivot point on this side, it falls, like it turns like this, right? It turns like this, isn't it? Correct.
Yeah.
And the second example, as soon as I put my pivot point this side, turns like this, correct? On the other side. If I
Yeah.
put my pivot point at the center, it remains at the center, correct?
Yeah.
It remains in equilibrium. Remember the word equilibrium, isn't it?
Oh, yeah, that's
But
right.
as soon as I put my pivot point here, it turns like this. As soon as I put my pivot point here, it turns like this. All right.
Yeah.
Let me explain you the question in a diagrammatic form. I have shown you the practical understanding of the question. Now I will explain you the question again. So the question is very simple in front of you. The question is something like this. First case, this is my rod. Assume it like a rod, okay? Assume it like a rod, okay?
Mhm.
So when you keep the pivot here, this is my pivot, right? It is in equilibrium, isn't it?
Yeah, that's right.
The second example, what happens is when you put the pivot here, let's say this is a rod, and when you put the pivot here, you must have noticed the rod is actually trying to rotate like this, right? Correct? Correct? Everyone?
Yes, yes.
Perfect. Let's take the third one. Third case. This is your rod. This is your pivot. And now you have to tell me the rod is trying to rotate like this. Correct? Reason.
Mhm.
What is the reason for all this? Why is this happening? That's my question. Why is
Because
this
of
happening?
the mass.
Can you elaborate why in the first case it's not happening?
Well, at this moment, there is no any kind of force. The only thing that make it rotate is the mass.
Or you can see the weight, right?
Yeah.
Okay, very good, good start. So there is a concept of center of mass, correct? Center of mass, right?
Yeah.
What is the meaning of center of mass? I can assume that on the entire mass of the rod is at the center, correct?
Yes.
So if the entire mass of the rod is at the center, I can say the entire weight is acting like this, correct?
Yeah.
Agreed?
Yeah.
So now focus. So see, in the first case, the diagram would look something like this. If I draw the force diagram of the rod, right? I hope you understand the force diagram. Drawing all the forces acting on the rod, right?
Yes.
So the first force is gravity, correct?
Which is weight, kind of.
Very good, weight. And the second force is because of my hand, right? My fingers.
Need force.
Correct?
No,
My
normal
fingers.
force.
Normal force, correct. Normal force, reaction force, right?
Yeah.
But my pivot is also at this point, isn't it?
Yes.
So don't you think the torque because of my weight is also going to be zero, and the torque because of my normal force is also going to be zero? Agreed?
Yes.
So here the net torque is zero, correct?
So it's called equilibrium.
Exactly. That's why it is equilibrium, not rotating, right?
Yes.
But in the second case, what happens? Let us understand.
Yeah.
In the second case, what happens is normal force is here, right? Correct?
Mm-hmm.
And gravity is at the center. Weight is at the center, right?
Yes.
But the pivot is here, correct? The pivot is here, isn't it?
Mm-hmm.
So torque because of
Mass times
n
gravity.
is equal to 0, right? Correct. Torque because of n is
That's
0,
right.
right? But
Mhm.
but do you think the torque because of force weight is 0? No. This produces a torque, right?
Yes.
This produces a torque in which direction? Clockwise or anti-clockwise?
Clockwise?
Exactly. So don't you think there is a net torque in the clockwise direction now?
There is a network.
And if there is a net torque in clockwise direction, my system will rotate in the clockwise direction. I hope this clearly makes sense.
Yes.
Try to do the third one now, quickly, on your own. Try
Okay.
to do the third one. Exactly similar. Exactly similar.
Okay. It goes through anti-clockwise.
Sorry? Correct. Very good. Very good. Very good. So you're trying to say it is creating a torque in anti-clockwise direction, right? Correct?
Yeah.
Because the pivot, the force is here. The pivot is here. The gravity is exactly at the center. The torque because of this pivot is 0. This is 0, right? Normal force. But this will produce a torque in this direction, right?
Yes.
That's it. Question done. I hope now you are able to understand what this torque does, right?
Yes.
Very easy. Very easy.
Yes. Yes. It's
Okay.
so easy.
Any doubts in this? Any doubts?
No, there isn't.
Okay. Are you aware of this thing called a seesaw?
See, so I've heard about it, but I don't remember
It's a small
that.
game, right? It's a small game in the park where there is a rod and there is a pivot. Okay.
Okay.
For example, there is a heavy man. Let's take what is your weight? What is your weight?
Hmm?
What is your mass?
55 kilogram.
Okay, let's take it 50. Let's take it 50, right?
Yes.
And let's take you are here. You are sitting over here, correct? 50.
Mm-hmm.
You are 50 kg. And then there is a heavy man who is sitting here. Okay, he's 100 kg. Can I say you can balance this man in this situation? You can balance, right?
No.
No? I will tell you why you can balance. See, I'm sure you must be afraid because the man is very heavy, right?
Yes.
So what is the gravitational force acting on you? Can I say 500 Newton? Let's say G10, correct?
Yes.
What is the gravitational force acting on this man? 1000 Newton.
1000. Yes.
So can I say this pivot will create a reaction of 1500 Newton, right? In upward direction. Agreed?
Yeah, I agree that.
But can I say torque because of this is 0, right?
Actually, yeah, you can. That's right. Because I guess the man is closer to the
Very
center.
good. Very good. So with the help of a bit of smartness, you can actually trick this man, right? See,
Yes.
let us say if he's at a distance of 1 meter, then you go at a distance of 2 meters.
Meter.
And see, you can literally hold this man, correct?
Yes.
So you don't need to have a bit of weight in you. You need to know a bit of physics about you, right?
Yes.
So greater the arm, this is called as arm length. Okay, this particular length is what called as arm length. Okay, arm length.
Mm-hmm.
I hope you agree with this.
Yes.
Okay, so greater the arm length, greater will be the torque, and you can hold a bigger thing.
Okay.
Any doubts in this understanding?
No, there isn't.
Okay, please note it, everyone. Any doubts?
No.
No.
Okay, let's do the last question for the day. Okay,
Okay.
fine. So let's take an example. I have a rod, a bigger rod. Okay, a bigger rod. All right.
Mm-hmm.
And this is my pivot. This is my pivot point. Okay. Let us say
Okay.
there is 100 Newton object at a distance of 2 meters. Okay.
Mhm.
Then there is a 50 Newton object at a distance of 1 meter from here. Correct. So don't you think these two wants to rotate the system anti-clockwise, right?
No, that's right.
Now the question is, I want to keep the rod in equilibrium, right? My goal is to keep the rod in equilibrium. So tell me, to keep the rod in equilibrium, I will have to attach some force here, right? Correct?
Yeah.
Let us say I have a 50 Newton object. I only have a 50 Newton object. I don't have any other object, right? So you have to tell me at what distance from the center I should attach it so that my system is in equilibrium.
3.
3?
Yeah.
No.
meters.
Don't be easy. It's not that easy. Think about it. It's not that easy. Trust me. Go with the concepts. For equilibrium, what is needed? For equilibrium, what do we need? Tell me. What is the condition? Net torque 0, right?
Yes.
And for net torque to be 0, can I say total clockwise torque, right? Total clockwise torque equals total anti-clockwise torque, right?
Yes.
Now tell me, which all forces are creating clockwise torque? Only this force, right?
Yes.
And what is the torque? This is just 50 into x, correct?
Mm-hmm.
Do you agree with me?
Yes. Yes.
Similarly, can I say these two forces are creating anti-clockwise torque?
Yes, you can.
So tell me the value. What is the torque because of 100 Newton force? Quickly. 100 into
2/200.
very good. What is the torque because of 50 Newton force?
50, which is 250. 250.
No. 50
No,
into
like
3. Come on.
oh, 3. Yes. Yes.
This was a trick for you. You have to find the distance from the center, right?
Yes.
Yeah.
So now do the calculation, do the math. 50x equals to 200 plus 150, right?
150,
Yeah.
which
So what is x? 350 upon 50, which is nothing but 7 meters. So see, this is the physics behind this. This is how you can do it.
okay.
I hope this is very clear.
Yes, yes, it was.
Any doubts in this session?
No.
Are you sure?
Yes.
Yeah, sure.
Okay. So what should I continue in the next class?
For now, I guess this
Moment
is
of
the
inertia.
kind.
Yeah, you're saying something. Please continue.
For now, I guess this is kind of the topic that we really needed to understand because it's one of our part of our final exams. So on the next day, we'll just have a new topic that we're gonna learn, which is tomorrow.
Good. So tell me, our next class, what do you want me to continue then?
Okay, right now, I don't know what kind of topic are they gonna teach us on the next day. So
Okay.
we
So
just
we will do
tell
moment of
you.
inertia. Moment of inertia.
Oh yes, stay. I
Yeah.
forgot
About
the moment of
inertia.
inertia.
Perfect. Perfect. So I want you to revise and come. Okay. Try to read a bit and come before the class.
Okay.
Okay. I'm sure you will enjoy better. You will understand it in a much better way. Like the way you
Okay.
understood it right now. Okay.
Yeah.
Okay.
Okay.
Fine. So I'll see you in the next class. Thank you very much. Take care.
Thank you, Mr.
Yeah. Bye.
Bye.
Right.